In many problems related to mechanics, we cannot restrict our attention to the analysis of the motion of a single point mass, but we need to study the motion of a system of point masses or bodies approximated by point masses that are simultaneously in interaction with each other. We can consider the system formed by the Sun, the Earth and the Moon or the Solar System itself as a system of point masses apart from the rotation of the Sun and the planets about their axes. In both cases there are mutual interactions between all the members of the system due to gravitational forces. Two spherical bodies or balls of masses m1 and m2 connected with each other in a fixed stand by springs with negligible mass can also be described as a system of point masses. The forces F1 and F2 are simultaneously exerted on the bodies by the stand, whereas the forces F sub 1 2 and F sub 2 1 represent the interaction between the point masses. Here the mutual interactions between the members of the system are due to the elastic forces produced by the deformation of the springs. Based on these examples, let us consider a system of point masses m1, m2, ellipsis, mn, and denote the position vector of the point mass mi with respect to a reference point O by Ri. Let also Vi denote the velocity of the point mass mi, where the momentum pi of the point mass is given by the product of its mass mi and its velocity Vi. The net force F bar I acting on the point mass mi is equal to the vector sum of all the forces exerted on the point mass, that is the sum of the forces F sub ij exerted on the point mass mi by the point mass mj, plus any net external force acting on the point mass mi. Then the fundamental equation of dynamics for each point mass governing the motion of the system of point masses is the following. The mass mi times the second order derivative of the position vector Ri of the point mass mi with respect to the time t, is equal to the net force F bar I acting on the point mass, where the index I of the members of the system runs from 1 to n. The left-hand side of these equations can also be written as the first-order derivative of the momentum pi of the point mass mi with respect to the time t. These equations state that the acceleration or the rate of change in the momentum of each point mass in the system is given by the net force exerted on the point mass by the rest of the point masses in the interacting system plus the external forces acting on the system. The net forces acting on the point masses do not necessarily point in the directions of the instantaneous velocities of the point masses changing under the effect of these forces, as shown in the figure. Since the fundamental equations are vector equations, they represent 3 times n differential equations for a system of n point masses, where the unknowns are either the coordinates of the position vectors or the components of the momentum vectors as functions of time. If we attach a Cartesian coordinate system to the reference point O, we can expand all the kinematic quantities in Cartesian coordinates. Then the 3 times n fundamental equations state that the mass mi times the second-order time derivatives of the coordinates x, y and z of each point mass mi, are equal to the corresponding Cartesian components of the net force F bar I exerted on the point mass. Similarly, we can express the 3 times n scalar equations as the first-order time derivatives of the Cartesian components of the momentum of the point mass mi, given by the Cartesian components of the force F bar I acting on the point mass mi. If all the instantaneous forces acting on the point masses in the system are known, then an initial value problem can be formulated and we can determine the motion of the whole system. The initial values are either specified by the 3 times n initial coordinates and the velocities of the point masses or their initial momenta. By solving the initial value problem of 3 times n differential equations for the system of n interacting point masses, we can describe the motion of the system in terms of position vectors, velocities or momenta changing in time. Since we need to know the explicit form of the forces describing the interaction between the members of the system and between the system and its environment, first we study the nature of the forces. By applying a proper classification of the forces acting in the system, we will able to prepare the formulation of general theorems, which provide important information on the motion of the system although they do not determine the motion completely. As already stated, the forces acting on the point masses can be divided into 2 groups. The internal forces acting between the point masses in the system and the external forces due to bodies outside the system. For example, let us consider the system of the 2 point masses m1 and m2 representing the balls connected to each other in the standby springs. The external forces acting on the point mass m1 are the weight given by the product of the mass m1 and the gravitational acceleration g, and the force F1 exerted by the stand as the spring connecting the point mass and the stand is stretched. Here the stand does not belong to the system of point masses and it is considered an external body acting on the system. Similarly, the external forces acting on the point mass m2 are its weight given by m2 times g, and the force F2 exerted by the stand pulling the spring used to connect the point mass and the stand. The internal force acting on the point mass m1 is the force F sub 1-2 exerted by the point mass m2 pulling the spring between the point masses, whereas the internal force F sub 2-1 is exerted on the point mass m2 by the point mass m1 pulling the spring from its other end. Considering the general case, we denote the net force of the external forces acting on the point mass mi by Fi, and F sub ij represents the force exerted on the point mass mi by the point mass mj. Then the force term in the right-hand side of the fundamental equations can be written as the sum of the forces F sub ij describing the interaction between the point mass mi and mj for j equals 1 to n, but not equal to I, since the point masses do not act on themselves, plus the external force Fi. As a result, we can formulate the equations of motion of a system of n point masses m1, m2, ellipsis, mn with the position vectors r1, r2, ellipsis, Rn with respect to a reference point O as follows. The mass mi times the second order derivative of the position vector Ri of the point mass mi with respect to the time t, or the first order time derivative of its momentum pi, is equal to the sum of the internal forces F sub ij exerted on the point mass mi by the point mass mj from j equals 1 to n, expect I, plus the net external force Fi exerted on the point mass mi by bodies that do not belong to the system. Here the index I runs from 1 to n. Considering the case of the free and constrained motion of a point mass, we can talk about a free system of point masses such as the solar system, or a rigid system of point masses such as the example with the balls connected with springs where the motion of the point masses is restricted by constraints. 2 point masses m1 and m2 at a fixed distance d sub 1-2, called rigid rotor, also form a rigid system of points, where the only constraint is the one stating that the distance between the 2 point masses is constant during the motion of the rotor. With respect to a given reference point O, the position vectors r1 and r2 of the 2 point masses can be represented by their Cartesian coordinates in a coordinate system attached to the reference point, and we can express this constraint in a mathematical form. That is the sum of the square of the differences between the Cartesian coordinates of the position vectors of the point masses is equal to the square of the distance d sub 1-2 between the point masses m1 and m2. The degrees of freedom F for the motion of 2 point masses is 2 times the number of the coordinates describing their instantaneous positions, that is F equals to 6. The one constraint imposed on the motion of the rigid rotor reduces its degrees of freedom to 5. We have already seen that freely moving rigid bodies have a degrees of freedom of 6 since 3 points of the body are needed to determine its position and orientation, which are given by 9 coordinates, and 3 constraints state that the distances between these points are constant. Rigid bodies can be considered as rigid systems of point masses, and in general, any system combined from rigid bodies forms such a system where constraints are imposed between the points of the different rigid parts in the system. Although this approach cannot be applied in a direct form for systems of infinitely many degrees of freedom, such as liquids, the theorems proven for systems of point masses in the next section will still hold for systems of infinitely many degrees of freedom. Besides dividing forces into internal and external forces, we can use other criteria to classify the forces exerted on rigid systems of point masses. We can talk about the aforementioned free forces acting on a given system such as weight or gravitational force, elastic force, or frictional force, and constraint forces replacing constraints imposed on motion that are not explicitly given, for example the contact surfaces of rigid bodies sliding or rolling over each other. As a result, we can write the equations of motion of a system of point masses in the form stating that the mass mi times the second order time derivative of the position vector Ri of the point mass mi in the system, is equal to the vector sum of the net force F sub naught I of the free forces acting in the point mass mi, and the net force F naught prime of the constraint forces exerted on the point mass. Both free forces and constraint forces can be internal forces and external ones. For example, the force exerted on the tennis ball by the ground while as it rests on the ground is an internal constraint force, but if we consider the ball itself as a system, then the force produced by the ground will be an external constraint force acting on the system. These classifications of forces enlisted here are crucial when we formulate general theorems on the motion of systems of point masses. Before presenting these general theorems, we note that the scalar form of the equations of motion of a system of point masses can also be expressed in curvilinear coordinates. We already defined the cylindrical coordinate system which we apply to describe the kinematic quantities of a system of point masses. If we attach such a coordinate system to the reference point O, we will be able to represent the position vector r of any point mass in the system by its cylindrical coordinates, such as the radial distance ρ of the point mass from the z-axis, the polar angle phi, and the coordinate z of the point mass. Other kinematic quantities, like the velocity v and the acceleration a of the point masses, and the force F bar acting on the point masses can also be described by their components written in a cylindrical coordinate system. The left-hand side of the equations of motion depends on the acceleration a of the point masses, that is the first-order time derivative of their velocity v or the second-order time derivative of their position vector r. When we studied kinematics, we determined the components of the acceleration of a point mass in a cylindrical coordinate system. We found that the radial component of the acceleration a is given by the second-order time derivative of the radial distance ρ, minus ρ times the square of the first-order time derivative of the azimuthal angle phi. The azimuthal component of the acceleration is equal to ρ times the second-order time derivative of phi, plus 2 times the first-order time derivative of ρ times the first-order time derivative of phi. The z component of acceleration is simply given by the second-order time derivative of the z-coordinate. These expressions can be substituted into the components of the equation of motion for each point mass in the system. Then the radial component of the equation of motion of the point mass mi states that the mass mi times the radial component of the acceleration of the point mass is equal to the radial component of the net force F bar I acting on the point mass mi. Similarly, the azimuthal component of the equation of motion states that the mass mi times the azimuthal component of the acceleration of the point mass is equal to the azimuthal component of the force F bar I acting on the point mass mi. The z component of the equation of motion is the same as in the case of the Cartesian coordinates, that is mi times z double dot is equal to the z component of the force F bar I acting on the point mass mi. Although the radial and azimuthal components of the equations of motion are more complicated than the equations of motion written in Cartesian coordinates, they can be simplified if the motion of the system of point masses exhibits a cylindrical symmetry which the cylindrical coordinate system is adapted to. For example, if the radial distances ρi of the point masses in the system from the z-axis are constant during their motion, that is they move over cylindrical surfaces around the z-axis, we can drop the radial component of the equation of motion, and omit the term with the time derivative of the radial coordinate ρi in the azimuthal component of the equations of motion. The other curvilinear coordinate system frequently used in mechanics is the spherical polar coordinate system, which can also be applied for a system of point masses to derive the scalar form of the equations of motion of the system. By attaching a spherical coordinate system to the reference point O, we can express the position vectors of the point masses in terms of the radial coordinate r, the polar angle theta, and the azimuthal angle phi. The velocity and the acceleration of the point masses together with the force acting have the corresponding expressions in spherical polar coordinates as well. As in the case of the cylindrical coordinate system, we determine the acceleration of a point mass in a spherical coordinate system. The radial component of the acceleration is given by the second-order time derivative of the radial coordinate r, minus r times the square of the first-order time derivative of the polar angle theta times the square of the sine of the azimuthal angle phi, minus r times the square of the first-order time derivative of phi. The polar component of the acceleration is equal to r times theta double dot times sine phi, plus r dot times theta dot times sine phi, plus 2 times r times theta dot times phi dot times cosine phi. Finally, the azimuthal component of the acceleration is given by r times phi double dot, plus 2 times r dot times phi dot, minus r times the square of theta dot times sine phi times cosine phi. As in the case of the components written in cylindrical coordinates, the components of the acceleration in spherical coordinate system contain the second-order time derivative of the corresponding coordinate, but they are functions of the first-order time derivative of the other coordinates as well. We can substitute the expressions obtained for the accelerations of the system of point masses into the equations of motion for the radial, polar, and azimuthal coordinates, where the left-hand side is equal to the corresponding components of the net force F bar I acting on the point mass mi in the spherical polar coordinate system. Although these equations are even more complicated than the equations written in cylindrical coordinates, they can be simplified if the motion of the point masses in the system has a spherical symmetry. For any system of point masses moving such that their distance from a given point is constant, the coordinate system can be adapted to this symmetry. As a result, the radial equations can be dropped, and the time derivatives of the radial coordinates will vanish, reducing the equations of motion to the terms containing the derivatives of the angular coordinates.